In this video, we'll look at more derivative shortcuts. That is, constant multiplied by a function, there's a rule for that, and the sum difference rule. The first shortcut rule we'll talk about is very straightforward. It's the constant times a function. And so if f of x is defined by some k, which is a constant, a real number, multiplied by some other function, then if I want to take the derivative of f with respect to x, well, k doesn't really affect anything, right? The only thing that's affected is g. So that means my rule is very simple, straightforward. If I want to take the derivative of f with respect to x, I just leave the k alone because nothing happens with the k, and I take the derivative with respect to g. So the only thing that really affects how f changes with respect to x is g. Therefore, this is the rule that we have. If we have a function, we want to take the derivative of it, and it's defined as a constant multiplied by a function, I simply get the constant multiplied by the derivative of that function. The second rule we'll look at in this video is the sum difference rule. Again, very straightforward. If I define f as the sum or the difference of two functions, that is g of x plus h of x, or g of x minus h of x, I've just written them both together in one expression here, then the derivative of f is simply going to be the derivative of g plus the derivative of h, or the derivative of g minus the derivative of h, depending on what we have here for a combination. Okay? So in fact, this is the sum difference rule, that f's derivative at x is going to be g's derivative at x plus h's derivative at x. Or, if they're defined as the difference, it'll be g's derivative at x minus h's derivative at x, okay, depending on whether it's the sum or the difference. Okay, so in other words, the derivative is a linear operator. In other words, it's going to operate across plus or a minus symbol. So now let's look at some examples to see how these rules work. So the first example is I've defined f of x as 5x squared. So notice I've got a constant here. This is like my k, right? It's just a number. It's 5. And this is like my g of x. So in other words, it's a constant multiplied by a function. And we already know by the power rule, that was one of the shortcuts we already talked about, how to compute the derivative of that. So I can compute the derivative of f of x, the first example. If I take the derivative, remember the constant just stays there, nothing happens. So I rewrite the 5, and I multiply that by the derivative of that second function. But we know the derivative of x squared. Remember, by the power rule, the 2 comes down, that's left in front as a coefficient, and we reduce the power by 1, so 2 minus 1 is 1. So the result is going to be 2x to the 1 power. Right? And so once we simplify this a little bit, we take the 5 and we multiply it by that 2 to get 10. And of course, we never usually write 1 as an exponent. So our answer is 10x. Okay, so we used this shortcut rule, constant multiplied by a function. Similarly, number 2, notice that this is defined as the sum of two functions, right? There's the first function, there's the second. This is like my g of x, and this is like my h of x. Again, I know the derivative of x, and I know the derivative of x squared, right? They're both polynomials, ultimately, or monomials, I should say. So what I'm going to do is I'm going to go ahead and differentiate f with respect to x, remembering the sum rule. The sum rule says that if I want to differentiate f, I simply differentiate each of its constituent parts, one by the other. It's the sum of the derivatives of the pieces of f. So this should be just equal to the derivative of g, but the derivative of this first function is just 1, right? So this is 1, plus it's the derivative of h. But the derivative of h is going to be 2x. We just did that in the previous step. So this is 1 plus 2x. Therefore, the answer is 1 plus 2x. That's using the sum rule. Let's look at a third example. In this case, I've got a function defined as the difference of two functions, okay? So I'm going to use really a combination of the two rules we talked about. That is, I'm going to use the constant multiplied by a function rule over here because there's a constant and there's a function. And I'm going to use the difference rule because, look, I've got the difference of two functions. So again, I can identify the pieces here. This is like my g of x, and this is like my h of x. So in some sense, f is really g minus h. But remember, by the difference rule, the derivative of f is simply the derivative of g minus the derivative of h. So let's go ahead and compute the derivative. So the derivative of f with respect to x is just going to be, well, it's the derivative of g minus the derivative of h, and g is defined as a constant multiplied by a function. I'm going to use the constant multiplied by a function rule. Remember that I just leave 2 alone in the front, the coefficient stays alone, and I differentiate the x squared. So what I get here is 2 multiplied by, well, the derivative is we take the 2 down, leave the base alone and reduce the power by 1. 2 minus 1 is 1. Minus the derivative of x cubed. Remember, again, we're using the power rule, so the 3 comes down, leave the base alone, and reduce the power by 1. 3 minus 1 is 2. So now I sort of make it look a little nicer, simplify. I get 4x minus 3x squared. That's my answer, okay? The great thing about this is, once we have these few basic shortcut rules for differentiation, I'm now able to differentiate a huge class of functions. In particular, I can differentiate any polynomial. Again, once we have these simple, basic shortcut rules, we can differentiate any polynomial just using a combination of the rules that we've talked about. That is the sum difference rule, the power rule, and the constant multiplied by a function. And of course, the derivative of a constant. So here's a polynomial, and you can come up with all sorts of different examples, but here's a nice polynomial. A polynomial means it's made up of a bunch of monomials, a bunch of single terms with powers. Okay, so a bunch of power functions essentially combined together with sums and differences. So I can differentiate this function now. The derivative of f with respect to x is, well, all I've got to do is just differentiate each piece term by term, because we know that by the sum difference rule, I've just got to differentiate each one of the pieces. And each piece is really a power rule, possibly with a constant out front. Okay? So I can differentiate this. The derivative of the first term is, well, I leave the 2 alone. I reduce the power down by 1. Well, the power comes down. Reduce it down. Plus, I take the derivative of that one. Leave the sum alone, right? So the 4 comes down. It's 3 multiplied by 4. X to the 4 minus 1 is 3. And I take the derivative of that. The derivative of a constant is 0. So minus 0. Now, we don't write zeros, and we don't usually write 1 as an exponent. And I'm going to simplify by multiplying my coefficients out as much as I can. So this is going to be 4x plus 12x cubed. That's the answer. So it turns out, again, for any polynomial, I can go ahead and differentiate it once I have these basic shortcut rules.